Okay, so in this video, we would like to basically focus on motivating you, convincing you basically that why topological way of thinking matters actually. Okay, so why topological thinking matters. And I'd like to briefly comment over the second question also, that is it useful? So is this useful? Is the topological way of thinking useful actually? So before addressing these two questions, let's quickly recall some of the key points of the previous videos actually, the key discussion that we had in the previous videos. So imagine this is you, okay, and imagine these are the topological goggles actually. So let's imagine that these are topological goggles, and what happens is that when you put on these topological goggles, or as soon as you put on these topological goggles, everything that you see around yourself becomes extremely flexible. So all this world, all of these objects like that are in your sight becomes, elastic or extremely flexible. Okay, that you can stretch or shrink or fold as much as you like. Okay, extremely flexible. And eventually when you see through these goggles, like the things that around you, basically you start seeing really the fundamental structure of all these objects. Fundamental structure of all of the objects that you see actually. What does it mean? You don't look for through these goggles, you don't look the quantitative differences between the two objects, but you see the qualitative differences between the objects actually, or the qualitative similarities between the objects. So through these goggles, we have discussed this several times, that a line and a parabola and a spring would be basically the same thing, because all of these have a fundamental structure. Okay. Similarly, a sphere or a ellipsoid, okay, maybe a rugby ball or a bowl, without any hole, or a plate, okay, they all are same actually. They all are, as you can pick one of these objects and apply what you call the continuous transformation so onto them and turn it into the other. And then you also know that we also have discussed basically that like for example, that there are objects which are similar to each other, but there are also objects which are different from each other. For example, a sphere or a bowl or this ellipsoid is different from a donut actually. So if you pick a donut or a torus actually, so these two objects are not equivalent actually, because there is no essentially hole in the sphere, and there is one crossing in the sphere. And then we also know this famous example that like this donut is equivalent to the teacup actually. Okay, so it's equivalent to the teacup. Okay, so what happens when you put on these topological goggles, or you start looking at the things around yourself topologically, you start seeing the fundamental structure of the object. So this is what really is the summary of the previous discussions. Now, I would like to now move towards that, why this way of thinking, why topology matters actually. Okay, so why this topological way of thinking matters. Okay. So one of the key advantage of looking at the things topologically is that you can, study, the bunch of objects, or maybe a class of objects in bulk, actually, in bulk. So what do you mean by that? Imagine you prove, say, a theorem about, an essential property of, say, a line, actually. So you take a line and you prove a theorem about the line, okay? But that theorem is of the fundamental nature. We will later on see that, what do we mean by that, okay? So if you prove a theorem that investigates, say an essential property, a fundamental property of, say, a line, the same theorem is not only going to be valid for line, but it is going to be valid for this entire category of the objects, actually. It's kind of valid for all objects. So rather than studying line and a parabola and a spring and a, and an arbitrary curve separately, you just study them in bulk, okay? Like a property that is possessed by, for example, sphere, a topological property, possessed by a sphere is also going to be present in, say, a paraboloid or a bowl or any object that does not have a hole, actually, okay? So one of the benefit of topological way of thinking or topological way of proving things is that you can, rather than studying the individual objects, you can study the objects in bulk, actually, okay? You can study the class of the objects, actually. So that's really is the key thing. So let me demonstrate basically that, what is, for example, the advantage of studying the objects in bulk, actually. So for example, let me quote a theorem. It really is a classification theorem. Okay. Classification theorem. Classification theorem about 3D closed surfaces. Okay, so like a classification theorem about 3D closed surfaces. Roughly, this, you may assume that, okay, by 3D, this closed has a technical meaning, but for time being, you may assume that these are the 3D surfaces with the finite volume, actually, okay, with the finite volume, or maybe those surfaces are roughly the finite surfaces, okay? Anything that does not have a hole is basically a sphere, okay? So anything that does not hold is a sphere. So for example, I mean, we know that, like, okay, this is a sphere. We know that if you take, for example, a piece of rock, okay, you take a piece of rock, that's also a kind of a sphere. You take, for example, a watermelon, okay, that watermelon is also a sphere. You take, for example, a plate, actually, the plate does not have a hole, okay, so that's also a sphere, a kind of a sphere, okay. And if you take, for example, I don't know, a bowl, okay, and that's also, is an example of a sphere, but the bowl should not have any hole, actually, okay, according to this classification result. So in other words, you can put all of those objects that you see around yourself, okay, that does not have a hole, you can put it in a category of a sphere, actually. You can put them as a single object. They all are basically same, okay. And if an object has, for example, a one hole, okay, then that object, no matter what object is that, so if it has a kind of a one hole, is a torus, actually, or a donut, actually. It's basically a donut. All right. So, like, a cup is a donut. You take a cup, actually. So a cup is a donut because it has this one handle with it. So you take a I don't know, a jug, okay, something like that. That's also you know, a donut or anything. Just look around yourself and, you know, take an object and try to see the number of holes in it. So if the number of hole is 1, it is basically a kind of a donut actually. And how about if, for example, something has 2 holes or 3 holes actually? Okay, so you know, you can have something that has 2 holes. So if there is something that has, you know, 2 holes in it, okay, 2 holes in it, you may treat that object as a double donut, or 2 donuts glued together. Okay, so you know, you take a donut with 1 hole and you take another donut with other hole, and you know, you glue them. You know, with gluing is a, you know, a mathematical operation. We're going to see it, but it's not a continuous operation. And you know, create what do you call a double donut. Okay, so just look around yourself and try to find, for example, those objects that contains 2 holes actually. For example, if you have a window, okay, or maybe a wall, you know, if you're sitting in a room and it has, for example, you know, wall, obviously it's going to have wall, and if it has 2 windows through it, then this wall is basically a double donut. Okay, so it's like 2 donuts, 2 toruses put together. And similarly, you guessed it, if you have 3 holes, it's like, you know, 3 donuts, you know, put together, glued together actually. Okay, so it's like glued together, 3 donuts glued together. So and so on and so forth. So according to this theorem, this classification theorem, this beautiful theorem actually, everything that you see is either a sphere or a donut or a combination of donuts actually. That's it. Okay, so the things that you see around yourself are topologically, basically, you know, either sphere or donut, or the all kind of variety of surfaces around you. Okay, finite volume surfaces, closed surfaces around you. Like all those surfaces can be put together in 3 categories, that either they are sphere, or they are donuts, or they are combination of donuts, or, you know, toruses actually. So that's really the interesting way of looking at you know, looking at the things actually. Okay, and obviously if you prove, for example, a topological or a fundamental property about, for example, torus, then that property is, you know, also going to be in all of the objects, you know, that are equivalent to the torus actually. Okay, topologically equivalent to the torus. So, you know, interesting, very interesting. Okay, so here's a little exercise for you. Okay, and exercise for you to look at this picture. Look at carefully this picture and identify that, you know, in this picture, which of the objects are, you know, equivalent to spheres, and which of the objects are equivalent to, you know, torus, and which of the objects are double donuts, and, you know, so on and so forth. Okay, so like this is one of the exercises for you. And not only with this exercise, just look around yourself and try to apply, you know, this theorem, and try to put, you know, the objects that you see around yourself in these, you know, 3 categories actually. I would like to move towards the second part of the video, in which I would like to talk about that is the topological way of thinking useful. So is it useful actually? Okay, and I would like to try, you know, by giving you some non-trivial examples, I would like to convince you that the topological way of thinking is really useful. So the first example that I would like to talk about is the relationship of, say, the topology and understanding the expansion of the universe actually. Expansion of the universe. So we quite often hear that, okay, the universe is expanding at an accelerating rate, the galaxies are drifting away from each other, and the rate at which they are drifting away from each other is increasing. So it's expanding. And from this expansion, you also interpret or infer what the so-called Big Bang cosmology. Okay. So this famous Big Bang cosmology. Naturally, so whenever we think of expansion, actually, so we see that, okay, something is expanding, but it is expanding within something, actually. So if the universe is expanding, so you can ask a natural question that it is expanding into what? Okay. And the answer is that it is expanding into really nothing, actually, which seemed a bit strange answer in the beginning. But let me try to explain this through an example, actually. Let's start with really presenting an intuitive but a wrong picture of the Big Bang, actually. Okay. So as a layman, I mean, if you for example, intuitively think that how the Big Bang happened is that, okay, I mean, maybe that all of this stuff was concentrated at one point, and this point has what you call this infinite density, and so on and so forth. And a time came, something happened, and a bang happened, and then the matter that was trapped in this point is just flies off in all directions, and eventually the galaxies formed, and now the galaxies are going away from each other in all directions, actually. Okay, but this picture of Big Bang is not correct, actually. Why? Because this assumes that there is already kind of existing a space in which this expansion is happening, actually. While we know that at the moment of Big Bang, or before the Big Bang, there was no notion of space and what do you call time. The time and the space, they both emerged at the instant of what you call Big Bang, actually. Okay, so when we say that the universe is expanding, so it's really expanding into nothing, actually. So there is no empty space in which the universe is expanding. Now, obviously, you're gonna ask that, okay, if it is expanding into nothing and it is expanding, then what is the meaning of this expansion, actually? Now, this expansion is, in order to understand this expansion, we have to think a bit of topologically, actually. In order to understand that how universe is expanding, maybe we have to speculate about the topology of the universe. In other words, that what is the shape of the space, actually? What is the shape of the universe, actually? So some of the scientists, based on experiments, speculate that maybe we are living on a flat universe, and maybe who knows? I mean, who knows? Maybe we are living on a sphere, or maybe like the entire universe is spherical. In that case, it is going to have some interesting kind of properties. Or maybe we live on a donut, or maybe a double donut. Who knows? Okay, so we have no idea about the topology of the entire universe, actually. But we know one thing for certain, actually, that no matter what topology, no matter what shape of the universe it has, we can understand the expansion of the universe in the terms of that shape, actually. But let's imagine that, for example, that the universe has is of the form of the double donut actually. Okay, like looks like something like this actually. Then what is the meaning of the expansion of then a correct picture of expansion of the universe goes like something like this, like that if we assume, for example, like I'm not saying that that the universe is like double donut actually, because we have no idea. Okay, the current estimates that maybe we're living on a flat universe. Okay, but let's assume that say if our universe looks like kind of a double donut actually, then what is the meaning of expansion of the universe? Okay, then the meaning of expansion of the universe is that the space itself start off being really small. Okay, start off being really small. All of the the matter of the universe was crammed into really this small point. Okay, it was crammed into a small point here, and then space expands very rapidly first actually. So it expanded at very higher, what do you call, rate, and eventually the matter kind of cools off and began to form galaxies, say like these spots that you see are the galaxies. The entire universe looks like a donut, but like these spots are galaxies. Okay, so all of these spots are galaxies. And now when we are saying that the universe is expanding, what actually it means is that the shape of the universe is really preserved, and the distance between the galaxies is kind of homogeneously increasing actually. Okay, so the donut, so the universe from really beginning, say if it was donut, it would be almost like a double donut actually. Okay, in which the distance between the galaxies, okay, distance between the galaxies is really increasing actually. And when you're saying that the distance between the galaxies is increasing, what does it mean? That the size of the donut is topologically increasing actually. Okay, so that's really is the correct meaning of expansion. Okay, and same would be the case with the sphere. So who knows, that maybe we are living on a spherical kind of a universe actually. So the first all of the matter was was in the form of this sphere, and then as time passed on the different parts of sphere, the galaxies formed, and then the galaxies are drifting away from each other. The space between them is increasing in such a way that the shape of the universe is still, what do you call, sphere. So okay, and keep in view, I'm saying again and again, I'm not saying that the shape of the universe is sphere. So I'm saying that if it is spherical, it would be spherical. And when you say that the universe is expanding, what does it mean? That this shape is expanding actually. Okay, this shape is expanding, and hence the distance between the galaxies and all this stuff is increasing. Okay, so maybe don't really trust on my kind of description of it. Probably a cosmologist would be able to give you a more precise description, but that's what is really the rough idea actually. If we are living on a, for example, a flat universe, okay, which is a current estimation of it, that which the most of the cosmologists agree actually, that probably we are living on a flat universe. We haven't observed the curvature up to this time in the universe. Okay, so then how does the what are the meaning of expansion of the universe? The meaning of expansion of the universe is that like, okay, if everything was first concentrated here, then the matter cools started to cool off, and then the galaxies were forming, and then galaxies are, drifting away from each other, in a very homogeneous way, in such a way that the shape of, this entire, enterprise is same actually. Okay, so this shape is kind of preserved actually, and because if you're interested in, like understanding this description of expansion of universe, or maybe the shape of the space, the entire space, in a more precise manner, you may read this beautiful book by, it's called The Shape of the Space by the Jeffrey Weeks. Okay, so we saw at least one of the interesting kind of a benefit of thinking topologically, or the topology, that we can understand basically the expansion of the theorem, expansion of the universe, because the expansion of the universe is essentially kind of a topological phenomenon actually. Okay, let's now move towards really the second example. Okay, to show that why, for example, topology is useful. So probably this would be abstract, bit abstract example. I'll not get into the more details, but I'd like to give you that, okay, where this topological thinking is being used, or topological tools are being used actually. So for example, we all know, I mean, I hope that you must have taken, for example, some courses in differential equations, or maybe partial differential equations. So it's like when you take a natural phenomena, okay, you take a natural process, okay, and you try to model this process actually, so that as a model, either you get a, an ordinary differential equation with some initial boundary conditions, or a partial differential equation with initial and boundary conditions, okay, or maybe some, system of equations that could be linear, could be nonlinear, so on and so forth. Okay, so what is the role of topology here? One of the key role of the topology here is that is the solution of this initial value problem, this ordinary differential equation, or a partial differential equation subject to some boundary and initial condition, or the system of equation. Does the solution of your model exists, and if it exists, is it unique? Okay, so often existence and uniqueness of the problem, okay, for a, say, abstract initial condition, can be done and dealt with, some kind of, topological tool or topological argument actually. Okay, let me give you, for example, a concrete example. So let's talk about, for example, Google actually. Okay, so we all know that, okay, Google, for example, you go to the Google, you put, say, a word, I don't know, Sukkur IBA University in the search box, Sukkur IBA University in the search box, then you immediately get what do you call, some websites, the links for the websites as a result actually. And interestingly, and lots of websites, and interestingly, you always observe, and you must have observed, that the top websites are the more relevant websites. And as you go down and see the lower links, they are not going to be as relevant as to us actually. Now the question is that how does Google knows that how does the Google knows that, okay, which website is important actually? Okay, so the answer is that Google uses its interesting example. Our algorithm is called the Google PageRank algorithm. Okay, PageRank algorithm. Not get into the more details of it, but it's really a kind of a, you know, algorithm that is based on, you know, the democracy model, actually. Democracy model. Okay. So for example, when you search, you know, Sukkur IBA University and say, for the sake of example, that like that word is found in 100 websites. Okay. Now, how to know that out of 100 websites, which websites is important? For example, 95 out of these websites contain, say, the hyperlink for, you know, www.ibasukkur.edu.pk. Okay, so it's like all of, the most of the websites are, for example, referring to this website, so it will know that, like, okay, like this website, the Google will know that this website is important, actually. But all of this is happening in kind of a mathematical way, actually. Okay, so you make a search, your word is found in 100 websites, then how to know that which website is important? Basically, Google, you know, creates, you know, a ranking for all of these 100 websites, actually. Okay, and each rank is a number, actually. So it creates a ranking of the websites, and each rank is a number. So every website has a rank, actually. So that website that has a higher rank would appear above, and the website that has a, you know, second highest rank would appear on the second list, and so on and so forth, actually. Okay. Now, obviously, you're going to ask that what is the role of topology here? Okay, the role of topology here is that basically when you make a search and you find, for example, you know, your word in 100 websites, Google roughly creates a problem. Okay, so it creates kind of a system of, you know, equation. Okay, something like this. Okay, now the question is that, does this system of equation has a solution? And that solution, which is this vector x, actually, which contains the ranks of the websites. Okay, does this x exist? And is this x that contains the ranks of all 100 websites, is it unique, actually? Okay, so you in order to prove the existence and uniqueness of, for example, the solution to this system, the Google uses the topological argument, actually. So topology roughly makes sure, topology is making sure that, you know, whenever you make a search, there is always a result, actually. Okay, making sure there is always a unique ranking of websites. Okay, of websites. I mean, if you really want to see this in detail, you can watch, for example, my playlist in functional analysis. Okay, and there you will find basically a detailed description of it, that how all this is happening, actually. Okay, and how the topology is making sure that there is always a ranking of the websites, you know, a unique ranking of the websites exist, actually. Okay, so next time, whenever you use, you know, Google, you know, say thanks to the, you know, topology, because the topology is making sure that whenever you are making a search, there are some results. Okay, and results in such a way that the more important results are at top and less important results are, you know, downward, actually. Otherwise, for example, if there are thousands and thousands of websites and there is no ranking of those websites, then you will be keep on looking on all websites to know that, okay, which website is important, actually. Okay, the Google is making my life easy. I know, you know, I haven't given a details of things here, but essentially that really is the idea. So this shows that, topology not only, rules our, universe, the physical universe, but it also rules our life. Actually plays a central role in our, in everyday life. Google is everyday life of ours, actually. Okay, so we will get into the, like all of these. These are some of these, for example, applications in more detail when we learn, the stuff more rigorously. At the moment, I know that I'm doing waving of hands, but I just want to motivate you that once you take topology seriously, there is a whole lot of thing, okay, in this modern world, which is based on the topological ideas, actually. Okay, we're going to talk about some applications, in, for example, about the geographic information systems, actually. Okay, so geographic info systems. Okay, GIS, that how the topology is used here. We will see, some of applications of topology in genetics. Actually, we're going to discuss them in lectures. Okay, and we'll also see, for example, some of applications of, topology and some very basic idea of topology in, for example, robotics, actually. Okay, and probably we'll also see some examples, in economics for the topology. So topology and topological ideas are almost everywhere. Okay, so I hope that I kind of gave you some, hints that, okay, why topology is important. Okay, it allows you to classify things. There are lots of interesting things which are written in this language. Okay, when you want to, for example, I mean, physicists especially use topology a lot. I mean, for the entire, general relativity and the quantum mechanics, the both of these foundations of physics, the quantum mechanics and, say, general relativity. Okay, it really, the both of the sciences are heavily reliant on topological ideas. General relativity, really assume that the space and time is a four-dimensional manifold, and a manifold is really a topological space. All of the quantum mechanics is being done in what we would call Hilbert spaces, and Hilbert spaces are, kind of topological spaces. So the topology and the topological spaces are, all around us. Okay, so I hope that, with all this vague discussions, I haven't kind of give you kind of precise description of it, because to precisely describe, the things that, kind of I have mentioned, you have to learn a bit of topology, actually. So we can and we will get back to some of these ideas later.